so now it's recording. So in QuantumESPRESSO, the input is structures in different blocks, right? Well, the first block we start with is a so-called control block. Right? We initiate a block by using this sign here. Maybe I can increase the font size, so it will be easier to read. Font sizes, I guess here we are. Select. Okay. And then it is important to say QuantumESPRESSO, where does my control block ends? We use this one. Okay. In the control block, we can specify the type of calculation we want to have. So we type calculation is a self-consistent field calculation, SCF, meaning we're only going to have a self-consistent density. It's not a structure relaxation. If you don't are confident now with what is a self-consistent field calculation, don't worry. We go into detail it in the next lecture. One line is then ended by a comma, and the next part we want to give is the restart mode. That is kind of practical because when a QuantumESPRESSO calculation ends safely, we can actually restart it from the last point quite easily by changing from scratch to restart. That will be of advantage later on also. For now, from scratch is fine. Then we can give the calculation a name. I call it H atom in a box. We need to indicate where QuantumESPRESSO can find the pseudo-potentials. This can be either the folder you are currently running your calculation, but I find it more practical to specify a directory that is always there. Right? I basically don't change that. So I say that is my home directory, user T, sudo library. I still need to create that directory, right? There's nothing inside there, neither it exists. The output directory is temp. This is where files other than the outlog will be stored. And end step is not relevant for us at the moment, but later when we do structure relaxations, right, we have that already there, so we can just using it. The next block is the system block. Also here, I start with the end sign and stop with this one, and in between I put in the details. I say we have the number of bands is equal to 5. Hydrogen has 1 electron. In solid state terms, that corresponds to 1 occupied band. To run calculations, we need at least the number of bands that are occupied plus a few more. Right? So here 1 would be occupied, and I give it 4 unoccupied ones. For hydrogen, that is not very expensive to do, and it helps the calculation run smoothly. E Pravez is to set the Pravez lattice. We put it to 0 because we have a big box in a cubic structure. So that is the most simple way to do. So n atom, that is important. That is the number of atoms in our unit cell. Then we need to specify the number of different elements. Here we have 1 element that is hydrogen. So we have 1. If we would have water, right, we would have 3 atoms and 2 elements, hydrogen and oxygen. But here, one atom calculation with hydrogen. Then one important parameter is the cutoff of the wave function. And a safe choice that is also not too expensive is 40. The unit here is Rydberg. And Rydberg, 1 Rydberg is half a Hadri. A Hadri is 27.21 eV. Therefore, a Rydberg is 13.62 eV. For the single atom calculation, I recommend this occupation that is computed with a smearing. The smearing is a Gaussian type smearing that normally works pretty nicely for isolated systems. If we go to solids, we might change that. So different types of system, when we also have a metallic one, right, we might need to adapt this part, right? And then we have so Gaussian is a Gaussian function, and the Gaussian can have different widths. And here we give a width of 0.01 Rydberg. There is, right, when you these last 3 options, there is not a strong, I don't have a strong opinion for these options, neither against these options. You make a choice, right? You see what you get. You would change, for example, the width of the Gaussian, because you don't want that your result depends on the width. It should be within physical limits. So don't put values like 200 or 1 here, right? It's too big, because the smearing will correspond to a temperature, and the temperature normally is around 300 Kelvin, which is around 25 millieV, right? And if you calculate now this value here, 0.01 Rydberg, that is a 130 millieV, right? Which is roughly in the order we want to have. When we increase the broadening, it helps the convergence of the calculation. But we don't want to overdo it, yeah. It's the way the occupation is. It's a bit solid state physics, right? So at 0 temperature, we would have a Fermi-Dirac distribution. We have states here, and we occupy them, right? We say occupied, 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 occupied. This one is not occupied, this one is not occupied. If we increase temperature now, this distribution will look like this. Then we say occupied, occupied, occupied. Not fully occupied, but a bit. And that is a tiny bit occupied, right? So now the Gaussian broadening says, instead of the Fermi-Dirac, we put the Gaussians here, right? Around also the Fermi level. And when we have now the width of the Fermi, the Gaussian like this, it will also be occupied. If it is smaller like this, then we will not occupy. We come to that in more detail. Right? But these are things we need to plug in. Right. And therefore this technical part describing the electronic, the way the electronic part is solved ends here. Then we have to enter a couple of details on when the calculation of the electronic parts ends. So we start again with this sign, and then first thing we enter is the convergence threshold. Remember, I showed you the energy difference that is converging slowly, right? Here we enter the threshold and we say 1.0 d minus 8 Rydberg. That is a safe value, pretty standard. Then we say how many iterations we want to have. Let's say 100. Sometimes, when you have a more complicated calculation, 100 will be not enough. then the program will tell you something happened. I couldn't converge my electronic states. I stop here, right? And then you, as the scientist, will say, okay, what can I do? You could, for example, give it 1,000 steps. Right? Give the program more time to find the solution. Right, and that is all I want to give you here. And we close that block again on this line. So we have given the type of calculation, described it a bit, told it where to find the pseudo-potentials, right? Described how we describe electrons and how to solve it, the electronic problem. Then we need to still discuss the structure, right? We just know now, okay, they're electrons, we solve them this way, we describe them this way, but we don't know how big is our box, nor where our hydrogen atom sits that is given here, right? These lines, these two lines indicate one hydrogen atom. So we now enter the cell parameters. And here we can specify the unit. So I like to work in Armstrong, right? Because Armstrong are easy for me, right? Bond lengths are normally 1 to 3 Armstrong. Atom size is a bit around in Armstrong. And then I enter a block of 3 numbers. So these are, because I specified I pravase, giving me full access to the control of the lattice in terms of lattice vectors. I specify here, I have one vector going 6 Armstrong in x direction. Right, I want to make a box, and the easiest box is cubic. Then I say my next vector should be in y direction. So it should be 0, 6, 0. And the last should be in z direction. So now I have an empty box, right? Good. So I want to place a hydrogen atom inside. So I start writing my atomic positions. Let me enter a few lines here, so we scroll that up. So my atomic positions, because I have periodic boundary conditions in a big box, I have only one atom, are arbitrary. You can put your atom in the middle of the box at coordinate 3, 3, 3, right, in Cartesian coordinates. You can put it at 0, 0, 0. You can put it at 6, 6, 6. You can put it at 12, 12, 12 in the next unit cell, right? It will automatically translate it back into like the box of the simple unit cell, the normal unit cell. So I, for simplicity, put it at 0, 0, 0. But my units, I also like to specify an Armstrong for the big box calculation. If we talk about solids, we can use fractional coordinates. But next time we will hear about fractional coordinates, real space coordinates, and all these things, right? Right? Okay. Then we are left to actually say what kind of pseudopotential a QuantumESPRESSO should use. Here we specify the location, but not the file in which we store the pseudopotential, right? We download a file, we place the file there, but if we download more than one file, what shall they do, right? So we need to specify the exact name of the pseudopotential, and we do that in the atomic species. We say for the hydrogen atom, here, right, H, mass equal 1, use H, optimized norm conserving Vanderbilt pseudopotential with the PVE functional version 1.0 UPV. Okay. if you change the name here, right, make a small h, QuantumESPRESSO will not know where this element refers to this element here, right? So these two things must match. So you either make them both small, or you make them both as a capital H. Right. Then the last line is about the k-points, because it's a big box calculation. We say that we only use the gamma point that sits at 1, 1. No, we have one gamma point in x, y, and z direction, so the grid has 1, 1, 1. If you put here 2, you will have 2 gamma points. Here you have 4. Now you have 8. Right? It's an automatic generation of gamma points. Of k points, not gamma points. So you only have one gamma point, and the gamma point lives at 0, 0, 0 in the Berührung zone. 0, 0, 0 is the center, right? Good. And with that, we have everything. Now we need to copy paste the remaining. I'm here. The pseudopotential. We need to download the pseudopotential, and we need to copy paste it here. You need to copy paste it in your folder, right? You have a username, right? So your home folder is different, and you need to adapt that. So that is now the test user home folder. You have your own username, place that here. Good, we do that now. I stop the recording.